We're here at Analytical Answers, a company which has been performing materials and failure analysis for more than 25 years. Over that time, they've completed over 50,000 analyses, a high percentage of which deal with surface chemistry and thin films. We will discuss some thin films today with Edward Norton, Technical Director here at Analytical Answers. He has been working in thin films deposition and materials characterization for nearly 20 years and would like to talk to you about the coatings on razor blades. Thank you very much, Ed, for sharing your expertise with us today.
Thank you very much, Christina. Today we're going to talk about how those shaving blades stay so sharp, and we're going to compare a number of different samples of these blades and talk about their differences, and we're going to do that with a couple of different analytical methods. So just a quick overview. I'm going to talk about properties of good razors, and we're going to talk about why we would want to add coatings to those razors. I'll give a brief description of the samples that I analyzed for this webinar, and then I'll go over what analytical approaches might be the most appropriate for analyzing very thin coatings. I'll go through the step-by-step analysis of one of the blades in more detail, and then kind of summarize the other blades in a little bit more brevity. And then I'll compare the analytical methods with one another just to show you why one is better than the other for certain types of samples, and then we'll go with a little summary. First, I would just like to mention that we do have 3 more webinars in our series between now and the end of the year. The next one is going to be called I'm Looking Through You. It's going to be talking about using transmission electron microscopy, which is our newest offering, and also scanning transmission electron microscopy to characterize ultra-small defects, structures, and composition. In November, we'll talk about polymer and composite failures in the webinar titled My Analyst Says I Have a Failure. And then in December, we're going to do something we hope that you find very exciting, in that you get to decide what the topic will be. We're accepting entries on our website through September 22nd. And if your topic is chosen, our gift to you will be 2 hours of your choice of a single analytical answers technique at absolutely no charge, and you can look at whatever you would like in that time period. So I hope we get a lot of suggestions in addition to the ones we already have, because I think everybody out there has some great ideas for what we could look at. So let's talk about what makes a good shaving razor. Well, I think it goes without saying, but I'll say it anyway, that they have to be sharp. But how can they be made so sharp? Well, they have a very fine-grained microstructure, which allows the blade to take a very fine edge, a very sharp edge. If you had an inappropriate microstructure, very coarse microstructure, it might not be able to be honed to quite that same edge. And razors are among the sharpest things made by man, with a tip radius down around 1/10 of a micron. A micron is, of course, 10 to the minus 6 meters, a millionth of a meter, or the thickness is around 100 nanometers, which is a nanometer is a 10 to the minus 9 meter. You also want that sharp blade to be quite hard, because you want that blade to hold its sharpness for as long as possible. But the problem is when you make them very hard, they also tend to get brittle. And so you also have to balance that with toughness. You want to make sure that the materials used in the base are tough, in addition to being hard. And so there's a balance between those. Another property that requires some balance in how they make the base materials for these blades is corrosion resistance. Every grade of steel is going to have a slightly different amount of corrosion resistance, and you can add certain things to the base metal to improve that so that it does not rust or corrode in its use. But as you tend to make blades harder, you actually tend to decrease the corrosion resistance. So they're asking a lot out of the materials in order to obtain these 3 functions, which help to preserve the sharpness throughout the blade's life. And so they do use special grades of steel, which have these properties. They do have to be very careful about how they heat treat them and anneal them in order to really make the blade the very best that it can be. The picture on the right here is just an example showing the different bevels that are ground onto 4 different blades, and all their sharp cutting edges are aligned on the right-hand edge of the photo with the arrow. And you can see that the second one from the top has a very, very long grind, and that's about 1 millimeter long, which is huge compared to the one on the very bottom. And that very long one is a very sharp blade, but it's designed for short duration use, like a scalpel, whereas the very short bevel, which has a lot more metal in it, is going to last longer because that's a shaving razor. And so, of course, depending on exactly the application, you'll have different grinds on these steels. So how can coatings help? Well, one thing we could do is improve the hardness. Like I said, if you try and make it too hard, you're going to be brittle, and you might lose corrosion resistance. So in order to improve the hardness, you can add some thin, hard coatings, which will be more durable than the steel by itself. And of course, that'll make the blade stay sharp longer. You can also improve the corrosion resistance of the stainless steels. And while stainless steel does form a thin chrome oxide layer to protect itself naturally, and that's what makes stainless steel stainless, you can add layers on top of that to further improve its corrosion resistance. And again, this is all helping the balancing act between hardness, toughness, and corrosion resistance that's part of the makeup of the base material. And there can be some additional benefits to having these coatings. It can improve comfort for making the way it slides over the skin. It could be used in marketing applications where if your coating is particularly striking, like for instance, gold-edged steak knives were all the rage in the 90s. And of course, they didn't have any gold in them. They had nitride coatings, which are of course hard and durable, but they were mostly marketed as gold-edged blades, simply because that attracts consumers' eyes. And of course, having a secret coating on your blade helps with patent protection and helps you keep a leg up over the other guy. So let's talk about the samples in an anonymous way that we're covering here. So I'm going to analyze the coatings on a number of samples. Most of the popular brand ones all had very comparable prices and features. And I'm going to call them popular brand A and B, and that's based on a sampling of just what's available in the aisle at my grocery store. And they were all 4 or 5 blade cartridges. I also analyzed for comparison 2 internet brands and 2 bargain brands where you can get 10 or 12 twin blade razors for just a couple of bucks. And so it'll be interesting to see how the much more expensive popular brands compare with the internet brands and with the bargain brands. So how can we analyze thin coatings? Well, we're going to talk about 2 different techniques here. We're going to talk about scanning electron microscopy with energy dispersive spectroscopy and scanning Auger microanalysis. Now, both of these techniques scan the surface with an electron beam, and they both give you high magnification images, just like any scanning electron microscope, but they analyze different outputs from the excitation of the atoms. So in the bottom picture here, what happens is the incident particle is your electron from your beam. It hits this core level electron and ejects it, leaving a vacancy. And then an electron from an upper energy level drops down to fill that gap. And that energy difference between those levels has to be given up by the atom. And in this case, it gives up an X-ray photon. And that's what we measure when we do EDS. Now, the same type of excitation and transition down occurs in the Auger process, but instead of giving up an X-ray, that energy is transferred to another electron, which is then ejected from the atom with a certain amount of kinetic energy. And by measuring the kinetic energy of that Auger electron, that's when we're doing scanning Auger microanalysis. And so they analyze very different particles, and that gives them very different capabilities in terms of depth of analysis. So how thin are we talking about here? Well, since the tip radius is small, the coatings need to be very thin to preserve its shape. So we're talking, again, the tips are down around 1/10 of a micron or 100 nanometers. So we need a technique which can analyze on that scale. So if we look at the picture on the right, we can see our incoming E-beam hitting this fictional surface, And the beam spreads out when it hits the surface into, this is classically drawn as a teardrop, but it can, depending on the materials and the energies involved, be more of a hemisphere. But in this photograph, this entire volume of material, the teardrop, is what gets excited by that electron beam. And everywhere that that beam hits, when those atoms get excited and then come back down to their normal state, they give off both X-rays and they give off Auger electrons. Now, X-rays, as everyone knows, can go through matter quite easily. So this entire volume, which is several microns deep in some cases, gives up X-rays. And so by doing EDS analysis, you're looking several microns into the material. And although Auger electrons may be generated deeper in, because they're low energy electrons, they can only escape from this very thin layer right near the surface, with a depth of about 4 to 50 angstroms, or just up to 5 nanometers thickness. So since we're looking at coatings that are only 100 nanometers thick, it doesn't make any sense to base our analysis on a technique which looks microns down. We want to look at something that looks nanometers down. So Auger is the clear choice here, which again looks at a depth of 4 to 50 angstroms or a couple of nanometers. So we're going to do this analysis primarily using Auger. And this here is our field emission Auger system. And it looks pretty cool. There we just saw the column and the analyzer, and now we're seeing the sample chamber. And so here we see the sample in the chamber, and we see the bottom of the analyzer, and that's how we do our Auger analysis. So again, we probe the surface with an electron beam, and we excite the emission of Auger electrons from the top few nanometers of material. And that analyzer I just showed you just measures the kinetic energy distribution of the Auger electrons. So what we end up with here is a plot of counts or intensity versus kinetic energy of those electrons, those Auger electrons that are being emitted by the sample. Now this plot here has actually been processed with a derivative function. The raw data that comes off the instrument is in non-derivative form, but the classic way to analyze the Auger data is in the derivative form. So here we see a spectrum of just your kind of standard base stainless steel. We see 3 large peaks for iron, a couple of small peaks for chromium, and small amounts of carbon and oxygen just residual on the surface. This particular stainless steel doesn't have any nickel in it, or we'd see a peak over here. And so this is just to kind of show you what a basic Auger spectrum would look like. And so we know the coatings are around 100 nanometers thick, potentially. And we also know that we can only analyze the top 5 with Auger. So how do we get deeper into the surface? And this is where we start doing ion sputtering and depth profiling. So in the Auger system, we have an in situ ion beam, which typically uses argon ions, but others can be used. And it removes material from the surface in a controlled fashion through ion beam sputtering. And so the beam rasters over the surface of the sample and removes material basically layer by layer. And it's a fairly slow process. The sputter rate for silicon dioxide, which is what we calibrate on, is 220 angstroms per minute, or 22 nanometers per minute. And this is actually a good thing that it's slow, because you can actually take very fine steps as you go through your material. Other materials will have different sputter rates, and we don't often know those, so sometimes we'll run standards of other samples in order to figure out what those unknown sputter rates are so that we can better calibrate client data. And so over on the right, we see a cartoon of a sample, a substrate with a red, green, and blue coating stack on it. And we can see that when we analyze the surface, we get this spectrum here. And then we could, in theory, sputter away for some fixed amount of time, and now we'll get a different spectrum deeper into the material. And then we could sputter again and look at another scan of material and analyze each of those layers. But the problem is you don't know what elements are down there until you get there. So we'll talk about how you can get a leg up on that in a minute. So when you set up a depth profile, you select the amount of material to be removed in each slice, each layer that you peel off the sample. And basically you pick a desired vertical resolution by setting a slice of either a tenth of a minute or a few tenths of a minute of sputter time per slice. And you have to select a value that's appropriate to the total thickness you're trying to get through, and also not to have too many slices that you can't get through the entire stack in a reasonable amount of time. And so you have to kind of balance infinite resolution with infinite time. Then you have to select the elements to be scanned. And in order to help us go a little bit faster so that we can get more vertical slices, we don't actually take a full spectrum generally at each slice. We just take windows around select elements. And so we'll pick a narrow window. This here is the scan of the surface of the blade edge. And here we see carbon and fluorine. And so this is from some of the organics that they put on the surfaces to add lubrication. And so we see a big carbon peak and a smaller fluorine peak. And so we'll set the depth profile to scan these elements, but there's going to be other elements in there that we don't know about. And so how do we find out about what's in there? Well, you can base it on prior knowledge of the sample. If you're doing quality control or R&D, you probably know what coatings are in the stack, and so we can program the depth profile based on what's there. But if you're doing reverse engineering of a competitor's sample, then you won't know what materials are in the stack. And so in this case, we're going to use EDS in order to figure out more about what's deeper into the sample. And so this here is an EDS scan of that same area on the surface of the sample. And while on the Auger scan, all we saw was carbon and fluorine, here we can see that we're penetrating all the way through to the substrate because we see iron and chromium. We see a quite appreciable niobium peak, and we see a very large carbon peak, which seems much too large for just the surface lubrication. So there might be a carbon layer in there mixed in. And so that gives us some information about what peaks we might want to scan for while we look at, in this case, sample 1. Interestingly, there's also an argon peak in this EDS spectrum. You don't usually see noble gases by EDS, so there might be some implanted argon from the processing that's used in order to make the coating on, in this case, sample 1. So we analyze all the blade edges using EDS in order to determine the elements present. And so it provides a starting point for the Auger depth profiles, but doesn't give us any information about layer thickness or order. And again, that's why Auger is better than EDS to figure out the individual layers. But in order to figure out just what elements might be present there to give us a good starting point, EDS was perfectly fine. And of course, these are all stainless steel, so iron and chromium are present everywhere. And so popular brand A, both the men's and the women's, had carbon and niobium in addition to the iron and chrome from the substrate. Popular brand B on the men's had carbon and titanium in addition to the substrate. And on the women's, they had molybdenum. Now, moly, it was only there in trace quantities, and molybdenum is often added to steels for an improvement in corrosion resistance, but we didn't see the large carbon peak or titanium or niobium like we saw in the other 3 samples to the left. When we look at the internet brands, we see basically iron and chromium with just a little bit of moly in internet brand B, and the bargain brands were iron and chromium. Now, just looking at the EDS data, you might think that a lot of these ones that just show iron and chromium or iron, chrome, and moly might not have much of a coating on them or might be just bare stainless. Especially you might expect that of the bargain brands. But we're going to find out by doing the rest of the Auger analysis. So now we put the first blade sample into the Auger system. And this is a scanning electron microscope picture on the left at 2000x, just showing that blade edge. And of course, when you look at a razor blade, it looks perfect and really sharp by eye. But when you start getting up to high magnification, you can see that the grind marks are still there. You can see a little bit of rippling at the edge here that looks like there might be 2 different materials there. And so as you go to higher magnification, there's a lot more detail that, of course, isn't visible to the eye. When we go into higher magnification on the right, we could see that I selected 2 spots for analysis here just to see if this ridge line near the edge was actually a different material or if it was just a topographical artifact. So spot 1 is about a micron wide and 5 microns long, and it's located only 1 micron back from the edge. And because we have a high resolution field emission Auger, we're able to target these very small areas and place them very close to the region of interest. And then spot 2 was similarly sized and just set back from the edge to look at that other material to see if there was a difference across that step. So based on the EDS data and prior experience, we're going to profile for oxygen, carbon, iron, chromium, and niobium. And so let's watch a depth profile. So this here is a video. It's sped up 60 times. So what took an hour to depth profile, you're going to get to see in about a minute. Here on the y-axis, we have just raw intensity counts. And in the x-axis, we have sputter time. And the red and the blue curves are chromium and oxygen respectively. And they track each other initially, most likely because they overlap. They're very close to each other in the spectrum. And we'll clear that overlap up in post-processing. But while we're watching the raw data, they're going to track each other fairly closely. So then we continue, and we see a peak in that chromium layer at about half a minute. And then after about 2 minutes of sputtering, we're into a carbonaceous layer. And this carbon layer could be amorphous carbon or it could be diamond-like carbon. Auger can't really tell the difference. You would need a technique like Raman, which can tell you more about the compound present in order to look at a very thin layer of carbonaceous material and determine if it's amorphous or diamond-like carbon. Based on the application, I'm going to just continue to refer to it as diamond-like carbon. That would make sense if you want a nice hard coating, something made out of diamond or carbon with a lot of sp3 bonding. That would be pretty hard. So we keep sputtering, and I'm going to pause it right here. This data is unprocessed and raw while we watch the profile, and there is a good reason for that. The data is not normalized in order to allow us to determine if we're missing an element. For instance, if we didn't think carbon was in the stack, we might have left it out of the profile. And then there would just be a complete empty part of the trace here in the raw data. But if you were looking at process data, all these traces that are down around the noise would, of course, be normalized up to 100%. As you normalize to 100% for processed data. And so you might not notice that you missed an element. So looking at the raw data during the profile is important. As we continue the profile, we can see that that carbon layer is quite thick, and it actually takes about 9 minutes to sputter through. And so it's either very, very thick, or conversely, the material could have a very, very slow sputter rate, and that makes it just look thicker in time. And then as the carbon drops, that niobium increases, and that's most likely an adhesion layer between the diamond-like carbon and the substrate. And that's the cyan right here is the niobium. And then we get into the stainless steel substrate. So we can take that data and we can process it. And just note with all these depth profiles that the surface is on the left axis at sputter time equals 0. And so the substrates or the bases are always on the opposite end. So here, as we enter the depth profile, we first see that there's a bump of carbon and fluorine on the as received surface. And again, those are those organic and fluorocarbon-based lubricants. And then that chromium layer is shown in cyan, and that starts to increase. And again, peaks at around half a minute to 0.8 minutes. And now that we've processed the data, we see that the oxygen no longer, which is in red, no longer tracks the chromium perfectly. We can actually distinguish that there's a surface oxide and a slight interfacial oxide in the chromium. So there's a little bit at the start of the deposition, and then the surface oxidizes from exposure to atmosphere. And so it's good that we can actually tell that independently from the processed Auger data. Then we go into the very thick diamond-like carbon layer, and of course carbon's in blue here, and it persists until about 9 minutes, 10 minutes, and then we start to see the niobium layer, which is in green. And then we get into the substrate material where we see iron, chromium, and carbon. Now the carbon here is actually quite high. A lot of stainless steels don't have that much carbon. In fact, in many bulk stainless steels, the carbon is so low you can't even see it by Auger. But this one actually does have quite a bit of carbon in it. And we'll talk about that later. So here, while you're doing these depth profiles, you can actually pause the profile and stop and take a survey scan. And so if we stop this profile at 0.8 minutes, we can take a look at the full spectrum and see that we have mostly chromium with just a little bit of carbon left because there's some layer mixing. And this allows us, again, to determine if we're missing any elements that might have been in the stack up. So then we sputtered a little bit more and we stopped the depth profile. And here we see we're in the diamond-like carbon layer. And there is a very, very large argon peak. And sometimes when you're doing argon sputtering, like we do in the Auger, materials absorb argon. But since we saw an argon peak in the EDS, I suspect that that's actually a very real feature of this coating, in that there's a lot of argon that gets absorbed into the film. And then we sputter to 10.5 minutes, and we get into that niobium layer at the interface. And that allows us to, again, see that there's no other elements in the depth profile that we might have missed. I mentioned that the carbon was very high after the depth profile. This is the 2KX image of the blade edge before sputtering. This is the same blade edge area after sputtering. You can see it has polka dots. It's got the measles or something. And if you do point analyses on these little black dots, you'll find that these are inclusions that are rich in chromium and carbon, and that's actually characteristics of these steels to help with their mechanical properties. And if we compare a scan of the bulk stainless steel, which looks similar to the scan I showed you before, where you have 3 iron peaks that are very large, a couple of small chromium peaks. If we look at the blue, which shows one of those little polka dots, we see that there's much less iron present and a very, very strong chromium and carbon signature. So those are little chrome carbide rich inclusions that help the mechanical properties of the materials. So let's just do a quick summary here. Spots 1 and 2 on sample 1 were the same. That was only a visual difference. And so the coating stack up at the very edge and 5 microns back was identical. Popular brand A women's was the same as popular brand A's men's. There was no real difference between the two in terms of makeup. The thicknesses were a little bit different, but not large enough of a difference to think that it was just normal variability. Actually, they were slightly thicker on the women's. And the substrate on both had those hard carbide inclusions, which improved mechanical performance of the blade. So let's just watch one more video because I like them, and hopefully you do too. This is on sample 3. And again, this is sped up 60 times, so instead of 45 minutes, it's 45 seconds. And here we start in a carbon layer. And again, this could be diamond-like carbon or amorphous. I'm going to call it diamond-like carbon because of the application. And while it's relatively thick, it is thinner than on sample 1. And again, also note there was no top layer of chromium here. Now this sample didn't have niobium. It actually has a little bump of titanium that showed up at the interface. And there was a little bit of titanium in the EDS spectrum, which allowed us to know ahead of time that that was going to be there. And then finally, we enter the stainless steel substrate. So when we look at that data after processing, we see, again, a almost pure diamond-like carbon layer. And then it transitions down after about 6 minutes with that little titanium adhesion layer right at the interface between the coating and the substrate. And then we go into the iron and chromium substrate, again with a fairly high carbon because of those chrome carbide inclusions. And that carbon layer that we found after sputtering varied quite a bit because sometimes the spot that was selected happened to sit on several of those little chrome carbides, and other times it sat on just one or just eclipsed a partial one. So there was a lot of variation in post-depth profile carbon concentration in the depth profiles. Okay, so now here's our results so far table again. And all three of these samples have some fairly advanced coatings on them. They're multi-layered, they're diamond-based, and that's not easy to do, and it's not cheap to do, but there's obviously a performance benefit to them, or else nobody would do them. So let's just calibrate our eyes on some types of blades that you might not think would be advanced coated. So let's look at kind of your classic double-edged shaving razor, and we'll look at a surgical scalpel, and we'll look at a single-edged razor. And no one can deny that these are going to be extremely sharp blades, but they are typically designed for much fewer uses than your commercial shaving razor, and that's probably why they don't have advanced coatings on them. Maybe. Let's find out. So when we look at the depth profile of the scalpel, we can see that this x-axis here is the same scale that was used for the first three samples, where it took almost 14 to 16 minutes to get through the entire layer. Here we can see that we were already through the layer in less than a minute. So I'm going to plot this on expanded scale. And here we can see that the carbon comes down very quickly. And so that was just some surface organic. And we go right into basically the iron and chromium of the stainless steel with just a little bit of a surface bump of oxygen. And so that's just going to be an uncoated stainless steel with its native passivation on it. And so while it may be a very sharp blade, it doesn't have any advanced coatings on it to make it more durable, but it doesn't really have to, because scalpels are typically designed for very short duration use. A surgeon might only make 1 or 2 cuts with each scalpel before he wants a fresh one. Again, now let's look at the single-edged razor. Again, the scale is expanded here because the layers are so thin, so the x-axis only goes out to 6 minutes here. Here, these are not even stainless steel. We don't see any chromium whatever in the substrate, and so there's no passivation layer. We go straight into a carbon steel, so we see iron and carbon, and there is just a little surface oxide, as would happen with any metal exposed to atmosphere, but there definitely isn't any coating of any kind on this carbon steel single-edged razor. This one was a little bit of a surprise. I expected the double-edged razor to actually be uncoated, just like the scalpel, but I was wrong. It does have a fluorocarbon-based lubricant package with some fluorine and carbon on the surface, but it does actually have an appreciable chromium layer on the surface, and that layer is combined with nitrogen, which is in green, at the top of the layer, and it transitions into an oxide at the bottom of the layer where it meets the substrate. So it's actually got a chrome nitride on a chrome oxide. It's fairly thin, being sputtered through in just over a minute, but it's still got a fairly advanced coating technology on it, which I found rather interesting. So if we just summarize this, the scalpel, again, very sharp, but it was just stainless steel with passivation only. The single-edged razor was a carbon steel with a slight surface oxide, but no coatings to speak of. And the double-edged razor was stainless steel with a thin chrome nitride chrome oxide. So let's go back to where we left off with our sample matrix for the commercial shaving razors and look at sample 4. This is popular brand B women's, and we can see here that just like the scalpel, all it has on it is a surface oxide. We have some fluorocarbon lubricants on the surface, but we go straight into iron and chromium and just a little bit of surface oxide. So we basically just have an uncoated, passivated stainless steel. So back to our summary of results. I found that very surprising on that fairly expensive blade, that it was just uncoated stainless steel. I thought maybe it was a fluke, so I actually reran that sample a couple of times and got the same result every time. And it was only a 4-blade cartridge, but it was still priced comparably to the 5-blade offerings, and so maybe that makes all the difference. But again, it was still an expensive cartridge, and so I was a little surprised that it was just uncoated stainless steel with simply its native passivation on it. So now I'm just going to quickly go through the remaining 4 samples. All of these had very thin coating, so they're all, except for the last one, they're all shown at the expanded scale. So this is the Bargain Brands blade, men's, and this is one that you might have expected to not have a thick coating on it, but actually it has a chromium layer that took over 1.5 minutes to sputter through, and just like the double-edged razor, the top surface was nitride, and the bottom interfacial region was oxide. So it also had that chrome nitride, chrome oxide stack up. There was actually a little bump in the carbon in between those 2 chrome layers, and I was a little surprised by that. I don't know, it's too thin of a layer at this scale to tell if that was an intentionally applied amorphous or diamond-like carbon layer, or if that was simply just poor cleaning in between process steps, where the surface of the sample was able to pick up contamination in between the chrome oxide and chrome nitride processes. Bargain brand women's, again, you might have expected these very, very cheap blades not to have any coatings on them, but this one has a fairly thick chromium layer on the surface that actually took over 3 minutes to sputter through. The surface had a little bit of oxygen in it, but that doesn't look like it's thick enough to actually be a chrome oxide. But rather interestingly, if we zoom in the green, there's a very, very slight bump in the nitrogen signature as well. And so I wouldn't technically call this a chrome oxide on chrome nitride because the concentrations are so low. But it is interesting that there was even any nitrogen in there. And this one also had a carbon bump. This was at the interface between the stainless steel and the coating. So this may just be related to surface cleanliness before coating deposition was performed. When we look at Internet brand A, we see that actually, although I took some steps to remove some of the surface lubricants before depth profiling, because it takes a while to burn through those to get to the layers, the fluorocarbon / organic lubricant package on this sample actually was quite tenacious and didn't come off as easily as it did on the other sample. So it was very well adhered. And then here we see there's a chromium layer on top of the stainless steel. And if we zoom in, we can see that there's a nitrogen peak, an appreciable one, followed by an oxygen peak. And so this is also a chrome nitride on chrome oxide coatings package on top of Internet brand A. And when we look at Internet brand B, this one was actually unique in terms of all the other ones had nitrides and oxides or diamond-like coatings. This one here actually has a carbide-based coating. So here we see the surface carbon from the organic lubricants and the fluorine drop down, and we come into this fairly thick layer of chromium and carbon before going into the substrate. And so this chrome carbide layer is another type of hard durable coating, but it's actually unique among all the other samples as they didn't really have carbides. And there was a little bit of oxygen at the interfaces that was picked up by the Auger, but there certainly wasn't any sort of oxide layers. So now that we've looked at all of our samples, let's just do a summary now that I can fill in the rest of the chart. All the samples had organic and fluorocarbon, probably a PTFE or a Teflon type coating on the surface. Auger's not good at identifying those. That's a job for FTIR and Raman. But those are typically nice lubricating coatings that help with smoothness and comfort. There was quite a varied result among the samples. I mean, we had 3 samples that were diamond-like carbon-based. We had 2 samples that were chrome nitride, chrome oxide-based. We had a chromium coating, a chromium carbide coating, and an uncoated. And that one actually, that one still surprises me. So if we examine all the depth profiles, we can measure the width of the peaks and determine what the sputter time was to get through all of those. And we could do that for all 8 of the samples that we depth profiled as part of our sample matrix. And if you were making relative comparisons between similar samples, you could just use this data. The popular A men's had 8.9 minutes of DLC, and the popular A women's had 10.8. And so since those are the same materials, you can make a relative comparison amongst a group of samples. But what we'd really like to have is a real thickness on these, because that'll give you better quality data in terms of what you're trying to understand about the coating process or the competitor's coating process. So you could estimate thicknesses using the known rate of SiO2, which again is what we calibrate on, but that's less than ideal because all these materials are likely to have very different sputter rates than SiO2. But at least it would give you kind of a ballpark. You would know that you might be dealing with tens of nanometers of material instead of microns of material. But instead of a depth profile standard, let's talk about doing cross-sectioning on one of these samples, the top one, in order to get some thicknesses to use as a kind of an internal standard on our study. So this here shows a mechanical section of a blade, and while metallurgically it shows those chrome carbide inclusions very nicely, the coatings are so thin and so delicate they don't really withstand mechanical sectioning very well. So in the absence of good sputter rate tables, in the absence of having a known standard, we're going to do cross-sectioning in a different method. And so here we're going to use focused ion beam milling, which we have talked about in other webinars, but I'm just going to use it as an example here. And so the focused ion beam works similar to an SEM, but does use a gallium ion beam to selectively erode material away. And it images like an SEM so that you can target very small features. And so you can just basically dial in where you want the cross section to be and literally target even sub-micron features. And you can prepare samples for lift out by performing two cuts which meet in the middle, and that's what this photo here shows. So here's the blade edge, just the last 20 to 30 microns of the blade edge, you can see right there. And of course on a major scale, you know, blades look very, very sharp, but of course when you zoom in on them, you can see the thickness, you know, it really makes a mountain out of a molehill. So here we've done two fib cuts that meet in the middle and leaves this freestanding little piece of the stainless steel blade that includes the very, very tip of the material. We also deposited a little platinum strip on the surface here to protect the coatings while we do the milling. And then you can go in with the beam and you can attach a probe to that little sliver that you made and cut it free at the base, and then completely lift this piece away and transfer it to a sample grid, which is a 3mm disc that you can then handle a lot more easily than you can handle something that's only 20 microns long. And then in the picture on the right, we have that little same piece now mounted on that sample grid. And you can see that the very, very tip of it, just the last couple of microns, have been thinned down. So this piece here, which is a couple of microns thick, has now been thinned down to just a fraction of a micron, down around 100 nanometers thick. And that allows you to get transmission images and transmission data, and allows you to do STEM and TEM. So when we look at the cross section in the high resolution SEM, on the right hand side we see a lower mag image where we see just the outermost 2 to 3 microns of the blade tip. And again, we can see that the radius of curvature here is very small, down around 1/10 of a micron. This entire length at the bottom of this image is 2 microns. So that's a very, very tight radius, which is what you want in a sharp blade. And then the light layer is the diamond-like carbon coating that we have on the sample. This thick layer up top is the protective platinum layer, which is not part of the blade. And then we can go in at higher mag and actually measure these layers individually and see that the niobium layer is 170 angstroms, the carbon DLC layer is 420, and the top layer is 140 angstroms, which was the chromium. And of course we see the stainless steel and the protective layers we put on top. So we can take the sputter times that we had from our depth profile on sample 1, we can take those thicknesses that we measured, and then we can calculate a sputter rate for those materials. And you can see that the sputter rate for that diamond-like carbon is actually quite low. So while you might expect a low atomic number material like carbon to sputter quickly, the very strong bonding in a diamond-like material actually gives it a very slow sputter rate. So now we can take that table of thicknesses, which were all in sputter time, and we can now convert that over to thicknesses in angstroms. And so the coatings, vary in ranges from down around just over 100 angstroms thick, or 10 nanometers, out to several hundred. Like this chromium is calculated to be around 360 angstroms on the bargain women's. And for instance, the chrome carbide could be estimated to be over 1,000 angstroms, and that's assuming that these carbides, oxides, and nitrides have a sputter rate similar to the chromium sputter rate we determined from sample 1. It's not the best approximation in the world, but it's going to be better than just using the silicon sputter rate. I said I would do a quick comparison. We're running out of time, so I'll do this very quickly. Here's the depth profile from sample 1. And here's an image that shows the cross-section that was performed on sample 1. And because we did STEM sample prep and thinned that sample down, instead of having several microns of EDS resolution, you can actually get it down to having hundreds of nanometers of EDS resolution. And so you can actually pick out these individual layers, the chrome, the carbon, and the niobium, just like we see in the depth profile, the chrome, the carbon, and the niobium. You can actually see that in an EDS line scan. However, you can see that the Auger does provide much better layer separation and is able to more clearly see individual layers and show that they're not mixing, and actually see subfeatures like surface oxides and interfacial oxides that you just can't see from the EDS scan. All right, so I'd like to summarize now, and I would like to say that clearly Auger analysis is especially capable at evaluating thin films. It is applicable to blades, obviously, but it is applicable to tools and cutting tools that have hard coatings on them, semiconductors, medical products, electronics and electronics packaging. Anytime you're looking for thin layers, whether it be contamination layers or deposited layers, Auger and Auger depth profiling is very capable. You can use it for quality control and reverse engineering of your competitors. You can use it in patent protection and litigation. If you have a failure during production or from the field, you might be able to use it to diagnose what may have caused that failure, some interfacial contamination, or you can use it for R&D. And so what blade should you buy? I am not going to answer that question based on Auger data alone. That's a very personal preference, and I can't tell you what to do there. Many other factors influence shaving comfort and blade performance. The lubricants, the fixturing. Some of these blades had pivoting heads, some had fixed, some had individually floating blades, individual suspensions, the handle and the grip. It's very much an individual preference, and so I can't tell you what to buy based on Auger alone. And so I would just like to say that no client data or materials were used. Actually, there's no permission needed. All this stuff came from the grocery store or from their respective internet vendors. And if you would like a custom webinar targeted to your particular industry or company, you can talk to us and tell us what type of samples and materials you'd like to look at, and we will set up a custom webinar where we can do it either on-site or remotely for you and your colleagues, and just contact us to set that up. Okay, I'm going to answer your questions now. If you didn't type in your question and want to email me later, you can reach me at answers@analyticalanswersinc.com, and you can visit our website where you'll be able to find archived webinars from the past and links to our techniques and methods and all the other good stuff that we do. And I'll just, while I'm answering questions, I'll just leave this upcoming webinars page up in order to help you guys out. So let's see what we've got for questions.
Thanks so much for that wonderful webinar, Ed. I see that Brian's question was already answered. with some of the slides that happened after his questions. So we've only got a couple more questions that came through subsequently.
So the first question was answered. Is this different than fib? I obviously incorporated fib later on into the information. The next question is, you showed the depth profiles. Can you also show lateral distribution of the elements in the coatings from the edge and along the edge? Well, on sample 1, spots 1 and 2 did have the same composition, but they were only microns apart. If you do go further back along the bevels, the coatings do taper off, and they're much thinner, so they're clearly selectively applied to the edges. And you could do either more depth profiles at specific distances, or you could do more cross-sectioning. Let's see. Could you use this coating information to identify who makes the various blades? Well, if you had known references from certain manufacturers, and I'm not going to reveal any of the manufacturers that I used today, but if you had known references and you wanted to compare an unknown blade to see who made it, you could track to see if they had the same coating stacks. That's not necessarily a guarantee that it was the same blade, because somebody could be copying somebody else's process. Does this work on machine tool surfaces? Yes, I did mention that in the summary, that it is possible to look at cutting tools. Oftentimes the coatings on those heavier duty cutters are much thicker than you would want to do Auger depth profiling on, so more traditional approaches like mechanical sectioning and EDS might be appropriate, but it really depends on the application of that machine tool. Let's see. Would the STEM-EDS or Auger techniques you showed tell me about other samples like this, like ceramics and oxide layers or polymers? Auger works best on conductive materials because it is an electron beam-based technique, so it doesn't really work well on ceramics or oxide layers on polymers, and so Auger has a hard time with those because of sample charge buildup. However, we do have another technique called XPS, X-ray photoelectron spectroscopy, which also does depth profiling and is as equally surface sensitive as Auger. However, it is a non-charge sensitive technique because it's using an X-ray beam as the probe, and it has inbuilt charge neutralization. So you don't have to worry about that as much. The next question is, what tool do you use to do STEM? Well, the STEM data I showed was actually done on our in-house field emission SEM, and so that was done at 30 kV, and that probably accounts for some of the breadth of some of those EDS traces and why they weren't narrower. We do offer work done on a higher kV instrument, up to 200 kV, where you would get much narrower line scans because of less scattering of the beam within the material. And so, so we do have that capability. I just didn't show any of that high kV work in this webinar. However, next month's webinar is going to cover all of that, where we talk about TEM and STEM. And then the last question is going to be, could the low levels of oxygen and nitrogen in some of the chrome layers be due to residual air in the manufacturing process? Absolutely. Some of those interfacial layers could be oxidation on sputter targets that was burning off, or it could be poor pump downs. Again, some of the surface oxygen is going to simply be from just atmospheric exposure. So in those samples where there was an appreciable amount of oxygen and nitrogen, 10, 20, 30%. Those are the ones where I said that those are more nitrides and oxides, but the ones where there was just a few percent of oxygen and nitrogen, that's probably, as you said, incidental, and I call those just metal coatings as opposed to nitrides and oxides. So that covers all of our questions so far. If anyone has any others, feel free to enter them. Otherwise, you could email us.
And that basically comes to close our webinar. We've got about a couple more minutes, literally 2 more minutes to this webinar. Thank you so much, Ed, for this really wonderful session. Really good coverage of a topic that has a lot of ramifications for industries other than the personal care industry. So thank you very much for that. And again, as Ed mentioned, you can email any follow-up questions that you have from this webinar to answers@analyticalanswersinc.com. We also encourage you to attend our upcoming webinars. October 3rd, we're going to talk about using transmission electron microscopy and scanning TEM to characterize defects, ultrastructures, and composition. November 7th, we are going to talk about analysis of polymer and composite failures. And December 5th, we want to remind you that is up to you, our audience. We have a form on our website. It will also be emailed to all attendees of this webinar for you to submit your own idea for an upcoming webinar. If your topic is chosen, our gift to you will be 2 hours of your choice of a single AAI analysis technique, absolutely for free. So we encourage you to get your suggestions in by the deadline, which is going to be end of day September 22nd. Again, want to thank you for coming to this webinar. It has been recorded. The recording will be sent to all attendees, all registrants, in fact, as well as posted on our website within the next couple of days. In the email with the recording of the webinar, you're going to get registration links for all of the upcoming webinars, which can also be found on our website on the webinars tab if you'd like to register right now. With that, I want to thank all of you for attending today's webinar and hope to see you again on October 3rd, November 7th, or perhaps using your idea on December 5th. Thank you very much. Have a great day from all of us at Analytical Answers.